The total revenue R earned in thousands of dollars from manufacturing handheld video game systems is given by the function highlighted, where P is the price per unit in dollars. Find the unit price in dollars that yields a maximum revenue and give the maximum revenue. Both of these will be in dollars. Okay, so our revenue function has a negative quadratic term, so that tells us that our graph will be a parabola that opens downward. We're going to be looking for maximum revenue. That's going to be the top of the curve. I marked that point P and R. P is our independent variable price per unit in dollars, and capital R is the revenue. Since we're looking for the maximum, we're going to find the vertex of this function. To find the vertex, aka the ordered pair at the top of the hill, our first number we calculate by using minus b over 2a. A and b will come from your function. B is the linear coefficient, that's 1800, so we have minus 1800 on top, or negative 1800 on top. In the denominator, we have 2 times A. A is your quadratic coefficient, and this one it's negative 25. Negative 18 over negative 50, the two negatives cancel. 1800 divided by 50 tells us that we have a $36 unit price. So $36 per unit. The revenue generated from that will be the revenue with $36 subbed in for P. So we're going to take negative 25 times 36 squared plus 1800 times 36. That works out to $32,400. So revenue is maximized when the price per unit is $36 and we have a max revenue of $32,400. Let's look at another corral problem. Excuse me. We looked at one of these in previous video. A rancher has 200 feet of fencing to enclose 2 adjacent rectangular corrals. In the diagram, you can see that we have a couple of X's across the front. That would mean we have a couple of X's across the back. Down the side, we have a total of 3 Y's, so to speak. So to account for all the fencing, we need to note that 4 X's, that's the front and the back total, plus 3 Y's, that's got to equal our 200 feet of fencing. We're supposed to write the area of the corrals as a function of X. Well, we know that area is length times width. The length, that's 2 X's, and the width is Y. So we can note that A equals 2XY. In order to get area in terms of X, we've got to sub out this Y. Solving our fencing equation for Y, we subtract 4 X's on both sides, and then we divide both sides by 3. Divide all the way through by 3. So Y is equal to negative 4/3 X plus 200 over 3. Now we can replace Y with negative 4/3 X plus 200 over 3, and that will get us into area just in terms of X only. So area is going to be negative 8/3 X squared on the first jump of distributive property, plus 400/3 X for the linear term. That's on the second jump. Since we're looking to maximize, let me scroll up a little. Since we're looking to maximize, we're going to find the vertex. Anytime you're asked to minimize or maximize and your function's quadratic, that means it has a dominant power of 2. You want to calculate the vertex. So for X, because that's our independent variable, we start with negative b over 2a. So that's negative 400 thirds as your numerator over 2 times negative 8 thirds in the denominator. The two negatives will make a positive. In the numerator, we have 400 thirds. In the denominator, 16 thirds. A complex fraction is when you have more than one fraction, or at least one fraction within a big fraction. Top fraction times the bottom one flipped over. Threes cancel. 400 divided by 16 is 25. Now that we know x, we can go back up to the fencing equation, plug in 25 for x, and that'll tell us what y is. Let's do that. I'm going to have to scroll back down, but I'm going to plug 25 into this equation. Okay, so negative 4 thirds times 25 plus 200 thirds. Use your calculator if needed. That's 100 thirds. Each corral, because there were two in the diagram, is going to be 25 by 100 over 3, which is 33 and a third. So that's going to be the measurement for each individual corral. If you had to measure the entire length and width, then you would say the entire length would be 50 and the width wouldn't change. Sorry about moving that on you. The width wouldn't change. But because there were two X's across the front, you might need to report that as 50 by 100 over 3. Now we're going to switch gears and we're going to move out of quadratics and into exponentials. Exponentials we haven't looked at all this year because they're kind of a totally different type of function. To be specific, exponential functions will have variables in the exponent. We're used to seeing terms like x, x squared, maybe an x to the third power. Those are algebraic terms. But now if you switch places with them and you start having 2 to the x or 3 to the x, those become exponential. There's a one-to-one property stating that if you can get a common base to be equal, then your exponents have to be equal. So let's use this one-to-one property to solve the following exponential equations. Upper left example, 2 to the x plus 1 power equals 16. We have different bases at this point. The left side we have a base number of 2. The right side we have a base number of 16 because it's 16 to the first. 16 just happens to be 2 to the fourth. Created equal bases. Now take your exponents. X plus 1 has to equal 4. And that tells us that x has to be 3. The example at your upper right, 1 half to the x power equals 128. There is a property that anytime you move a term across a fraction bar, the power changes sign. So this 1 half, if we move the 2 across the fraction bar, it will gain a negative. 1 half to the x is equivalent to 2 to the negative x. 128 is the product of 7 2's. If you were to multiply 7 2's together, you would get 128. Because we've created the same base number, we can take the powers and set them equal. Negative x equals 7 if x is negative 7. In our next couple of examples, well, let's start with that upper left one. I don't want to go too fast. We have 2 to the x minus 1 power equals 1/8. Since 8 is 2 cubed, we can write that as 1 over 2 cubed. Move this to the numerator, it becomes 2 to the negative third, matching base numbers. So by one-to-one property, the exponents have to be equal. X minus 1 equals negative 3 if x equals negative 2. Add 1 to both sides. Upper right example, and it's going to sound really weird, but in math, we have a number represented by e. So this base number e is legitimate. E to the 2x minus 6 power equals e squared. Immediately we have a common base number, and that's e. That's Euler's number. We'll discuss it a little more in the next video. But long story short, because the base numbers match, we could use one-to-one property, and that tells us that 2x minus 6 has to be equal to 2. Add 6 to both sides, 2x equals 8 if x equals 4. And then we'll look at one final example. Again, we have a base number e. E to the x squared plus 15 is equal to e to the 8x. One-to-one property tells us if the bases are equal, then the exponents have to be equal. So let's come over here. X squared plus 15 has to equal 8x. Because we have a quadratic term, I'm going to move the 8x over. Subtracting 8x's, and I'm going to drop it in the middle. We can't really combine it with anything because x squared and 15 are not like terms with a 8x. So move your 8x over, change its sign, and now we have x squared minus 8x plus 15 is equal to 0. This is a trinomial. We have it set equal to 0. You can choose to solve with quadratic formula if you like. I'm going to go ahead and just factor. X squared breaks down to x times x, and then I can easily find two numbers that have a sum of negative 8 and a product of positive 15. That's negative 3 and negative 5. If you add those two numbers, you get negative 8. If you multiply them, you get positive 15. This first factor is equal to 0 if x equals 3. The second factor is equal to 0 if x equals 5. And so those are two answers that satisfy that particular equation.